So we have physics PhD qualifying exam practice problem number 33. So let's go over this. So we have the following. Um, this is in classical mechanics. So part A, a particle of mass m moves in a smooth central potential v of r, where r is greater than 0. The motion is confined to a plane. Let the angular momentum magnitude be L cannot equal 0, and define the effective potential V sub EFF of R equals V of R plus L squared over 2mr. Assume there exists a circular orbit of radius R naught. So for letter A, we want to demonstrate the condition that R naught must satisfy for a circular orbit to exist. Express the angular velocity, capital omega, of the circular orbit in terms of V prime of R naught, M, and R naught. So let's go over this first. Here's part A. So the circular orbit condition, we have the effective potential is V sub EFF equals V of R plus L squared over 2mr squared. Circular orbit at R equals R naught requires V prime sub EFF of R naught equals 0. V sub EFF prime of R equals V prime of R minus L squared over mr cubed. So the circular orbit condition is V prime R of R naught equals L squared over mr naught cubed. And since L equals mr naught squared omega, then L squared equals m squared R naught to the fourth omega squared. So substituting into the circular orbit condition, V prime of R naught, that's going to equal m squared R naught to the fourth omega squared over mr naught cubed. And that is going to be equal to mr naught capital omega squared. My apologies for the omegas and the way they're drawn. Sorry about that. So capital omega squared equals V prime of R naught over mr naught. Omega, capital omega equals square root. We'll take the positive value of that. Positive value of the square root V prime of R naught over mr naught. And this requires V prime of R naught being greater than 0. So that's a circular orbit condition problem for that's part A. Okay, and just going back here, sorry about that, for part B. For part B here, we want to derive the condition for linear stability of the circular orbit under small radial perturbations and express the radial oscillation frequency lowercase omega sub r in terms of derivatives of V at R naught. Okay, so building on this, so back to this one, this page. So letter B, the linear stability and radial frequency. The radial equation can be written as motion in the effective potential. M, R double dot, equals negative V sub EFF prime of R. Let R of t equal R naught plus eta of t, where absolute value of eta is much less than R naught. And since we have the following here, V sub EFF prime of R naught equals 0. So V sub EFF prime of R naught plus eta, that's approximately V sub EFF double prime of R naught eta. So eta double dot plus lowercase omega sub R squared eta equals 0. Where lowercase omega sub R squared equals 1 over m V sub EFF double prime of R naught. So V sub EFF double prime of R equals V double prime of R plus 3L squared over mr to the fourth. Therefore, omega, lowercase omega sub R squared equals 1 over m times this quantity, bracket V double prime R naught plus 3L squared over m R naught to the fourth, close bracket. Using L squared over m naught cubed, that equals V prime of R naught. We get L squared over m r naught to the fourth equals v prime of r naught over r naught, and hence lowercase omega sub r squared, that equals 1 over m times this bracket here, v double prime of r naught plus 3v prime of r naught over r naught, close bracket. So the circular orbit is linear, so we could conclude the circular orbit is linearly stable if lowercase omega sub r squared is greater than 0, or equivalently v double prime of r naught plus 3v prime of r naught divided by r naught is greater than 0. Okay, so that's A and B. Now from here, going back, letter C. Suppose the potential is a power law potential. I'm sorry, letter C, that was letter D. Letter C, show that the ratio lowercase omega sub r squared over capital omega squared can be written as the following: r naught v double prime of r naught divided by v prime of r naught plus 3. Okay, and here, let's go over this. So we have our ratio that we're looking for here. Lowercase omega sub r squared over capital omega. So from part A, capital omega squared is equal to v prime of r naught over m r naught. And from part B, lowercase omega sub r squared equals 1 over m bracket v double prime of r naught plus 3v prime of r naught divided by r naught, close bracket. From there, therefore, we could say that lowercase omega sub r squared over capital omega squared equals 1 over m bracket v double prime of r naught plus 3v prime of r naught divided by r naught, close bracket, divided by v prime of r naught over m r naught. Now, getting rid of the m's, omega sub r squared over capital omega squared, that equals now r naught bracket v double prime of r naught plus 3 v prime of r naught divided by r naught divided by v prime of r naught, close bracket. So lowercase omega sub r squared over capital omega squared, that equals r naught v double prime of r naught divided by v prime of r naught, and then plus 3. Thus, lowercase omega sub r squared over capital omega squared equals 3 plus r naught v double prime of r naught divided by v prime of r naught. And this expression physically requires v prime of r naught be greater than 0 so that the circular orbit has real angular velocity. And also, lowercase omega sub r squared is greater than 0 for stable small radial oscillations. Okay, so that is part C. And just going back here, part D. Part D, suppose the potential is a power law potential, V of r equals alpha r to the n, where alpha does not equal 0 and n does not equal 0. Determine for which values of n circular orbits exist and for which values they are linearly stable. Okay, so going back to this. So what we have here, power law potential, V of r equals alpha r to the n. We have V prime of r, taking the derivative there, it's alpha n r to the n minus 1. So a circular orbit requires v prime of r naught be greater than 0. And since r naught is greater than 0, this becomes alpha n is greater than 0. Second derivative here, the v double prime of r equals alpha n times the quantity n minus 1, r to the n minus 2. And using the ratio now from part C, lowercase omega sub r squared over capital omega squared, that's going to equal that 3 plus r naught v double prime of r naught divided by v prime of r naught. So computing r naught v double prime of r naught divided by v prime over r naught. That's going to equal r naught alpha n to the n times the quantity n minus 1 times r naught to the n minus 2 divided by alpha n r naught to the n minus 1. And that's going to come out to n minus 1. So lowercase omega sub r squared equals 3 plus n minus 1, and that equals n plus 2. So lowercase omega sub r squared equals the quantity of n plus 2 times capital Omega squared. For linear stability, n plus 2 is greater than 0. Sorry. And so n is greater than negative 2. And so from here we could say that circular orbits exist if alpha times n is greater than 0, and they are linearly stable if, in addition, n happens to be greater than negative 2. Okay, so that's part D. Moving along now, part E. So for part E here, it says for the same power law potential, determine the apsidal angle between successive radial turning points for nearly circular orbits, for which values of n are sufficiently nearly circular bounded orbits closed. Some say apsidal, some say apsidal. Okay, so for this, part E. So, yep. So apsidal angle for nearly circular orbits, the radial oscillation frequency is going to be lowercase omega sub r equals the square root of n plus 2 times capital Omega. The angular advance during the full radial oscillation is going to be this delta phi sub radial period is equal to capital Omega times 2 pi over lowercase omega sub r, which equals 2 pi capital Omega divided by lowercase omega sub r, which is going to equal 2 pi over the square root of n plus 2. So the apsidal angle between successive turning points is going to be half of that. So delta phi sub apsidal equals pi over the square root of n plus 2. So for the classical closed orbit cases, the two-power law, potentials for which all sufficiently near circular bounded orbits are closed, are going to be at n equals negative 1 and n equals positive 2. And these are going to correspond to v of r is proportional to negative 1 over 4, and v of r is proportional to r squared. So we could say the Kepler potential and the isotropic harmonic oscillator potential are the special closed orbit cases. Okay, so that's letter E. And now, just to read letter F. So for letter F here, suppose V of R is not to be a power law. Find the differential equation that V of R must satisfy if every sufficiently small radial perturbation about every stable circular orbit has lowercase omega sub r over capital Omega equals k, where k is greater than 0 is a constant independent of r naught, and we want to solve for the general form of V of r. So again, suppose V of r here is not to be a power law. Okay, so for letter F, what we could do is the following. General potential with constant. Here, lowercase omega sub r over capital Omega equals k. And it requires lowercase omega sub r squared over capital Omega squared equals k squared. So if we go back from part C, we use that 3 plus r v double prime of r divided by v prime of r. That's going to be set equal to k squared. So r v double prime of r over v prime of r, that's going to equal k squared minus 3. And v double prime of r over v prime of r, that's going to be k squared minus 3 over r. So if we go ahead and we let w of r equal v prime of r, then we could say w prime of r over w of r equals k squared minus 3 over r. Now from there, if we integrate, natural log of absolute value of W of R, that's going to equal K squared minus 3, that quantity, ln R plus C. So what we're going to wind up with when we perform the computation, W of R equals AR to the K squared minus 3. And since W is equal to V prime of R equals AR to the K squared minus 3. Integrating, and V of R is going to equal A over K squared minus 2 times R to the K squared minus B. R to the K squared minus 2, and then plus B. So that's a plus B there. And that is provided that K squared does not equal 2. So for K squared not equal to 2, V of R equals CR to the K squared minus B. I'm sorry, I don't know why I keep saying that. V of R equals CR to the K squared minus 2 plus B. And if K squared equals 2, then V prime of R equals AR to the negative 1. So we could say V of R, that's going to equal A ln R plus B. So V of R equals CR to the K squared minus 2 plus B, where K squared does not equal 2. And the logarithmic special case is V of R equals A ln R plus B, where K squared does equal 2. Okay, so that's all for this problem. Thank you very much, and have a great day.